Swayam Prabha. Digital India. Educated India.
We were discussing a few salient aspects of the vacuum assisted consolidation, particularly to reduce the preloads. As I just mentioned, these field trials have been conducted in many places and they have been very effective, and people indicate that, all the studies indicate that there is a significant potential for cost savings over the conventional surcharge placement, and for at least 4.5 meters height. Why it is that we know that it is 1 kg per centimeter square, or 1 bar or 100 kPa is pressure suction you can apply. So theoretically about you can get 5 meters or 4.5 meters or even 4 meters if your things are properly done. If the vacuum is very good, definitely one can go for about 4.5 meters equivalent pressure. So you do not need to really apply the surcharge, but then you can get the equivalent effect by having the vacuum. That is the meaning here. And how do you do this is something that we should see. What we do is that, because sometimes we should understand the construction sequence very well, because the implementation of the construction sequence is very important, and if there is a mistake in one place, it could lead to cascading effect, and then the whole project may have difficulties. In this technique, we have a drainage blanket, sand drainage blanket of about 60 to 80 centimeters thickness of the saturated ground to provide for working platform. Installation of drains generally 5 centimeters in unequal diameter, like whatever, as well as of relief wells from sand, we do that. Installation of closely spaced horizontal drains at the base of the sand blanket using a special laser technique to maintain them horizontal. In fact, all along that at the top itself, like you have horizontal drains, the thing is that you have this particular area, you need to collect all the water that comes at the top. Essentially we can only provide the drainage at the top, right. So we collect water, and then because of that thing we just collect all the water, and so we need these horizontal drains. And in fact people use lot of sophistication here in terms of using this laser techniques to maintain them that they are horizontal. And so they both horizontal drains and their transverse, they are all linked, and excavation of trenches around the perimeter of the preload area to a depth of about 50 centimeters below the groundwater level, and filled up with an impervious bentonite polyacrylate slurry for subsequent sealing of the impermeable membrane along the perimeter. In fact, as I just mentioned, we are trying to provide the geomembrane layer, right, because it should be a sealant. What you are trying to do is putting a sealant there, and then vacuum should not, that capacity should be very good. All that area, in that area whatever you are trying to have that area, the vacuum should be very effective, then only it is possible. So that is the reason when people have perfected this vacuum technology, then it has become possible. So what they are trying to do is that they are trying to have the sealing of the impermeable membrane along the perimeter, okay, whole perimeter it has been sealed. Transverse connectors are linked to the edge of the peripheral trench. They are then connected to a prefabricated module designed to withstand future pressure due to vacuum. Installation of the impermeable membrane on the ground surface and sealing it along the peripheral trenches. The membrane is delivered to the site, folded and rolled. Actually we have the geomembranes are normally delivered onto the site. Then actually sometimes the membranes elements need to be welded also, and they are sealed with bentonite polyacrylate slurry. The trenches are backfilled and actually filled with water to improve the tight sealing between the membrane and the bentonite aqua keep slurry. So vacuum pumps are connected to the prefabricated discharge module extending from the trenches. The vacuum station consists of specially designed high efficiency vacuum pumps. Actually vacuum pumps, the technology is so good nowadays, acting solely on the gas phase in connection with conventional vacuum pumps, allowing the liquid and gas suction. So you have this a process in which you apply this vacuum, and this is like the this is very effective, and people can conceptually design this using one can, if you want to really once how it works. So the objective has been to just create a balance between the preloading, preload, you do not want to have too much of preload, you want to take advantage of the effective stress increase. You would like to take advantage of the effective stress increase, so that the total stress net is increased. As I just mentioned, the total stress also increases. So this what is the actual concept that we have, and technology, if you want to say was it effective, yes, it has been very effective in many places, and the main thing is that it does not really have any stability issues, because particularly you are trying to get the thing is why you are going for this sort of technology is that in a place where there is a full of soft soil, to get preloading material is quite expensive. Maybe with water you can preload, but water density being 10 km per meter cube, and the people do it, all sorts of loads you need to apply, but then to get the loads you may have to get the aggregates from different places and all that, it is environmental issues. Okay. So that way what we mean is that vacuum consolidation technique has been quite effective, and you can also place a surcharge. So it has been, another advantage has been that it has an apparent cohesion in the soil layer, top layers also, as I just mentioned. If you make proper connections, you can also have some sort of apparent increase in the cohesion due to increase of the effective stress, and in a granular layer itself, like what you are doing is you are trying to create some sort of negative pore pressure. Negative pore pressure increases the strength of the soil. So if you understand this concept, yes, it is very easy to do this. So the experience indicates that within days after the vacuum pump is turned on, construction vehicles maneuver on the top of the membrane. In fact, as I just mentioned, during the construction process itself, like if you are trying to have these vehicles, they must be able to move around, and with little bit of suction, if you can increase the effective stress so that the vehicles can move, it is fine. You do not need to have big surcharge and also consolidation and effective stress increase and bearing capacity issues. You can just apply proper suction. What is the load coming from the construction vehicles onto the soil, you calculate, and if you are able to maintain higher effective total stress because of the vacuum, then it is fine. So you are able to you have a higher resistance, strength is higher than the load applied. So you can see that that combination can be done. So it is an effective technique that can be very useful for highly compressible soils, and it can be useful for about 4 to 5 meters, definitely very useful. And the experience in US and China has been that it is very good, and people have been working on this further. So I am sure that in the coming days people have particularly the geotechnical engineering professionals will pick up this technique, particularly in many of the developing countries. And actually there is another small nice case study here. In Europe, actually they have tried to use that in particularly on one of the applications. They were able to really replace the conventional surcharge preloading for the development of about 57,000 meter square of the area in some place, in one of the areas. So that way loading using this vacuum consolidation has been effective, and it is also very effective for places where you have soft soil sites with shallow groundwater table. One difficulty is that if you have stratified soils like different layers, then there could lead to some difficulties, but I think still people have been able to use this technology in a comfortable way. So I must thank many of the where I could take down some materials from this, and also the some companies and Hausmann book, which I took a lot of material, and also from the Soham geotechnical group, which have the prefabricated vertical drains material they were able to share with me. So now I would like to take on what is called the another lecture that will go, where we talk about dewatering. Actually, this what we did in the previous case was also dewatering, in the sense we removed water and increased effective stress. So dewatering is a standard means of increasing the strength of the soil, right. So what we do here is that, again we will talk about, even say in the conventional foundation areas, how do you do this. Maybe soft soils are there in many places elsewhere across the coastlines and some interior areas or in lake beds and other things, but how do you handle groundwater problems is what we will see now. And I would like to show you what exactly it means, and we will talk about some applications as well, some examples. And why do you need dewatering? Dewatering essentially is that, particularly in urban areas, when you are trying to construct or make excavations below the water table, and which are the difficulty is that it is very difficult to design the structures to take care of the hydrostatic pressures. Normally you design with gamma b into height, the pressure acting at any point is gamma b h square by 2, but then if you have water also, then water pressure also gets added to that, gamma w you have to add plus gamma w h square by 2 again. So the pressure is huge. So you do not want that to, you do not want to design for hydrostatic pressures. Essentially what we do is that we do not want to design for hydrostatic pressures, and we like to dewater the whole thing or see that the drainage occurs properly. That is our objective. So permanent dewatering systems are far less commonly used than the temporary or construction dewatering systems. In fact, permanent dewatering to maintain is not easy. Like in a building, you have to just continuously dewater, it is going to be expensive, the house owner will not be comfortable. So what we have to do is that we have to have some sort of systems which are very how do you dewater actually first, how do you maintain that, and see that the buildings are waterproof or they have a full drainage, all that we should see. So what are the common dewatering techniques? You must have seen in many places, we are familiar with them, like you have a sump, you have a trench, you have pumps, well points, deep wells with submersible pumps. So normally we use a combination of many of these things to dewater. Say for example, the water table is at the ground level, and you want to construct a foundation at 3 meters level. What are you doing? So you have to really take down the water table to below 3 meters, maybe 3.5 to 4 meters. So you have to make suitable calculations and see that okay, you can make calculations of how much of the discharge of water should be removed from the area, we have the influence area and all that, and how do you calculate, how do you store that water, how do you connect the pumps and also the pipes for all that we should understand, right. So sumps, trenches and pumps, one can handle reasonably a minor amount of water flow, and the groundwater table above the excavation bottom is say for example, you have an excavation level at 3 meters or some so the excavation you have a small height of maybe 1.5 to 2 meters, one can handle with this, and the surrounding soil is relatively impermeable. If the surrounding soil is very good, like it is a good drainage material, there is no problem at all. But if the soil is surrounding soil is not clay, like water is not going at all, so you have to remove the water, right. So some pumps are frequently used to remove surface water and a small amount of infiltration of the groundwater. Sumps and connecting interceptor ditches should be located well outside the footing area and below the bottom of the footing, so that groundwater is not allowed to disturb the foundation bearing surface. In fact, if you are trying to do the concreting, you want to have it dry. You go to say for example, somebody is constructing an apartment and basement, say first 5 meters there is no water, but after the next 5 meters there is a water table. Then that man has to take that foundation, he has to start from that point. So you need to dewater. Say for example, it's the foundation level is at -10, the water table should be much down, like -12 or -11. One should calculate, because it depends on the drawdown. You have to create a drawdown situation and see that, you know, when you are trying to place a concrete or trying to have this foundation bed, you know, you do not have a difficulty. Otherwise, you know, the thing is, if during the placement of the concrete for the foundation itself there is a problem of differential settlement, it is going to be very risky. You do not want that. So what we do is that we do not want, we want the water table below the bottom of the fitting. That is the important thing. And in the granular soils, it is important that fine particles will not be carried away by pumping. Actually, in sometimes what happens that you try to pump, so the fine particles, they have a tendency to come out, because, you know, because of the pressure that you have, harder particles or bigger size particles will stay back, but then the small size particles get collected. So you need to filter them out. Okay. So that is the reason why sumps may be lined with a filter material to prevent or minimize loss of fines. This is very important. This is what is an example. In fact, it is an initial water table level, and this you would like to lower the groundwater table. You have a system like this. Say you have a sump here, you have made a ditch here, you have a sump pump here. Actually, these are all I mean, in the sense these are all, you know, extracted from the technical memorandum of the US Corps of Engineers. Okay. It is a valuable document that one needs to see, and in fact this is also one of the contributions from many of the people, that they could make some of these ideas and useful to people who need dewatering. So that's pump sumps is one. Well point method. In fact, there is another important thing, like if the water table is somewhat, you know, it's the depth of water removal of water is going to be high. You need to go for, you know, say for example, below 3 or 4 meters, you need to have this. So in the well point system, what we do? We have a multiple closely spaced wells connected by pipes to a strong pump. You have a number of pipes connected to a strong pump. Then multiple lines or stages of well points are required for excavations more than 5 meters below the groundwater table. In fact, there was one site that I was visited, like below, next to the sea. For example, you are trying to construct a nice resort next to a sea, but you know, there is a water table all the time, right? There is all the time water, but you know, you are trying to construct the foundation. So you have to really, during the process of dewatering, you should have well points. Well points, we will see that, and it is a very elaborate preparation, because suppose you are constructing for about 1 year, during 1 year period all that dewatering should be perfect, like all the systems should be working correctly. Particularly there is a rainy season, it should be really, you have to see that it works very efficiently. So for example, there is a single stage well point system, like you have a well point here. Okay. So this is the original water table, and this is what the bottom of the foundation. So you lower the water table like this. Okay. So these are all connectors and all that. Okay. This is from Caltrans, California Department of Transport, and this is a header pump and all that. You can see a typical arrangement here. Yeah, this is a typical example. Like you have a static water table and you have a system like this. You have well point here, you have another well point here, and so the groundwater table, you can see that it has come down compared to the previous static water table level. So this is what we need to do. So there is another one which is called deep wells with submersible pumps. Here the pumps are placed at the bottom of the wells and the water is discharged through the pipe connected to the pump and run through the well hole to suitable discharge point. See, all the pumps are at the bottom of the wells and the water is discharged to the pipe connected to the sump. to the pump, and essentially we will see that they are more powerful than the well points and require wider spacing and fewer well holes. Used alone or in combination with well points, actually deep wells, you have to go for a very deep well, put a submersible pump, which means it can be, it's you can even put under water and all that. So you have a suitable discharge point, all that one should calculate properly. Actually you have, see, the thing is, depending on the depth and the water that you are expecting to be removed, you have different varieties of methods here, and it is very important that see, they are all flexible, like depending on the situation you must be able to see that the combination can be used. This is very important, because how do you dewater, and what type of soils can have what method. So for example, this is a grain set distribution, US Corps of Engineers. This is a fine grain set distribution like 0.001 to 0.01, 0.11. So this is all gravel, this is all sand, and this is silt and clay. You can see that if the material is like in this gravel, gravelly material, okay, subaqueous excavation or cutoff may be required. The thing is that sometimes if you have a cutoff wall, sometimes it may be alright, because the pore size being bigger and all that, and there is one case that but still there, you need to still dewater here. Here, particularly why I am mentioning is that what you call, there is a, you have to have what is called, you can see that there is some range of particles 1 to 0.1, where there is a gravity drainage, okay, like you can by gravity alone you can remove the water, right. And so here you have wells or well points, and essentially what you are doing is, you have a well point at the bottom, and it creates that suction, and the water starts going towards that. You are trying to create a field of a point of attraction, so that water goes towards that. It is not against gravity. One should understand that you are trying to see go to the lowest bottommost point and then try to draw the water. So in the process, what is that, you are trying to create a gravity field, and so that works very well for wells or well points. And if the grain size distribution, you have to do a grain size analysis of the soil area, and then if the grain size distribution is in this range, yes, definitely gravity is work, and well points and all these things will work very efficiently, like sand, medium fine to medium sands. But gravity, if the grain size distribution is little low, what happens? The gravity effects are not really that dominant, and sometimes if the grain size distribution is very less, like 0.75 microns or something, gravity drainage may not be possible. So you may have to apply vacuum actually, okay. You can see that you need to even align, you can apply suction pumps, you can have, even in the laboratory we have. So then if it is too much of fine material, electroosmosis, like the thing is that we know that the clays are negatively charged, and you try to remove some ions along with cations, water starts coming out, something like that. So you have electroosmosis also. In fact, a lot of work was done on these lines, and one should be able to understand that, yeah, is the method appropriate. Of course, is say for example, one should understand how do you design this well points, or wells or well points, or this system, okay. So we will see that some applications, yeah, this is a very important application. Again, this is you have some places this is maybe a basement, and there is a permanent groundwater control system. In places, some places what happens is that you need to have, like I have seen, you have to design the base of this like foundation. How do you design? Actually the thing is that there is lot of water coming up, you have to design for the water pressure, like there is an uplift pressure that is created. Suppose there is a 5 meters of water and then you go down, it is 5 meters into that unit weight of water, that much of pressure is coming up. So if you place a foundation there is so much pressure acting. So you have to design, say for example you have a raft foundation in some place, you have to design, people design for the uplift pressure also, that is called uplift pressure, right. So in big areas and all that, that's so people design, you have like as high as 3 meters 4 meters thickness of the concrete is quite common. In fact there are a couple of inquiries on how to reduce this thickness of the concrete. If when it is 2 to 3 or 5 meters it is too huge, how do I reduce this pressure, because I am designing it for uplift. Actually the uplift is the maximum pressure acting, and that is the worst condition, one of the conditions that I should consider, because the uplift should not be creating any problem. So in that case, this is an example, you can see that this is the initial water table, okay, and you have a pump and sump system, and assume that you have a, like there is a piezometers here, okay, there are 2 piezometers here. Then you need to have relief wells. Suppose actually this is a typical illustration of how it can be done, and there is an artesian flow. What they created was relief wells were created here, okay, relief wells. It means there is a, like you as you go down there is a lot of water, right, water pressure is there. So you would like to create all that removal of water pressure should be there. So you create some sort of sand drain type of thing, or you can even put a prefabricated vertical drain here. It is very interesting. Even this you can create a particular prefabricated any drain, and then see that the earth pressure, whatever is the water pressure it comes up, it gets released, and it comes as a water here, and then it gets pumped and all that, and then you can see that it just goes up to the pipe and then it gets discharged here. Is it not? It is very simple that say the estimation of water pressures are quite simple, like say you need to really gamma W into height or the depth. So for example the initial water here, the initial water table there is no problem, but you have brought down to this level and you are trying to put this foundation. So at least from here to this level there is this much of pressure, at least a few meters down that pressure will be created, and you should also release this artesian pressures, because there will be always these pressures that could lead to difficulties. So you should see that this is also released. So what happens in this process is that the water table gets lowered, over gravity flow. You can see that at this point it is at this level, then it goes like this, okay, all the water comes here, then it enters this sand materials and all that, and you have a system of this thing, and then it gets removed. And you can also see that it is all little it is made impervious, so that water table, in this case of course there is maybe impervious nature of silt, in the sense is okay. Essentially one can design a system of permanent groundwater control also, is what it shows. There is another example here, like you have a sandstone, alternate layers of this which can occur because of the depositional sequence in nature. You have alternate layers of clay, silty sand, silt, weathered sandstone, silt and all that. It is quite natural, and our objective is, like suppose you are trying to make a shaft, vertical shaft, anything, like you see that this is the thing. So you would like to see that again you create a deep well, okay, with the auxiliary, why this is vacuum system is required, as I just mentioned. You have clays also, clays and sandstones and all that, to increase the efficiency of the whole process. So initial water table level is here, okay. So you have a submersible pump here, then when it starts working, like the water table level can come down to this level, right. This is what it means. Yeah, this is what I was just mentioning, that you have what buoyancy effects on underground structures. So, structure bearing pressure maybe say 10 ton per meter square or 15 ton per meter square, but then there is an uplift pressure, right. So, you have to design this system properly, that is very important. This is another interesting example. In fact, for Bangalore Metro also they were trying to check up with us if this is possible. Recharge the groundwater table to prevent settlement. Actually, why settlement occurs is because you remove water. When the water is removed, what happens? There is a difference, there is a 2 footing here, and when you remove water, actually the rate of water removal is higher here compared to this. So, definitely there is an effective stress higher here than this. Definitely there is a tilt, sudden change in the effective stresses. There will be some changes because of the change in the delta sigma, you have more settlement. So, suppose you are trying to construct an underground station here, right. So, you do not want that say you are trying to construct a retaining wall here, right, you are trying to construct a retaining wall here, but then there is a water table here. How do you construct the retaining wall, and then you have a water table? How do you handle this? The metro line has to go here. It is a very complicated problem. What should be done is that say for example, I have actually we are able to do that to some extent. Say in some example I was able to suggest them. This is the water table, right. Now I would like to say I use actually soil nailing for retaining wall systems. Suppose I just put a nail here, like I can't put a nail here because there is already water, right. So what I do is that I just little the release, the dewater a bit and then put the nail. Okay. Actually, the thing is that we should do this nailing operation so fast that you can see. The thing is that the nailing sequence is quite fast, like you can excavate, put nails, excavate, put nails, excavate, put nails. Suppose this is, say for example, this 5 meters depth, I can dewater this whole thing in a process of very short time, and also insert nails and allow the water to go back, okay. Or sometimes additional water can also be pumped in to see that water table close to this foundation is maintained. In fact, you can even construct a cutoff wall here, see that this will not create too much problem. Say for example, if the water table goes down below this footing, that is a problem. So, you try to maintain that and see that it likes a tub of water is always maintained next to these footings of the same level. So, one can do this. So, but then one should be very careful. So, what I am doing here is you are trying to recharge the groundwater table to prevent settlement, right. This is very important. Is in fact L&T and MAE, I do not know what will happen to many of the projects. So, they are looking at it very seriously because you have so many existing structures already, and because of this metro operations there should not be any difficulty. So, one should be able to either isolate this area so that the water table changes are not will not affect this buildings, and also see that this is area is you have to do the retaining system also, okay. In the case of slope, how do you do this? It is very important again, because you know that this is a slope which exists and you want to calculate the slope stability, like already the initial original water table is here. So, when it is saturated water table, the problem is, it is not easy actually, water keeps on coming onto the surface, So, you are trying to make an excavation here. So, what you should do is that you have to really like again lower that, you have a well here, sufficiently lower it like this, okay, properly. You should be able to understand the geology of the site, properly, so that you put a proper well system here and also one sand drain here. Okay. So, this well is able to remove the lower the water table. This also helps to some extent. So, in the process what I am trying to do is that, say for example, you can see that in the absence of the well, maybe the water table is like this, right. But because of this sand well or a drain, you are able to little bit lower. So, in fact, if you are able to see that the actual lowering is much below this, this is actually toe of the slope. Toe of the slope is a very weak point in a slope. The possibility is that if water starts coming, then there could be a possibility of failure. So, we should really dewater to such an extent that water table is here somewhat. I mean, this is a typical example, and one can really do sort of a good dewatering systems on these lines. So, yeah, there is another example, as I just mentioned, grout curtain or cut-off trench around an excavation. Here grout curtain or the cut-off trench is, it can be with the bentonite, it can be with the it can be with cement slurry, sand cement plus bentonite. There are different slurries there. One can, the objective here is that this is a original water table, and this is the actual area that you want that water, it should be water free, right. You want to have this water free, like maybe you want to construct a big mall here, right. Let us assume that you are constructing a very big mall and you are trying to have a nice green settings here with some parking and all that and whatever. So, one can have anything, and what is that we did here, we can do here is that it is just that first thing is the water table level should be very much lowered, is it not? That is our prime purpose. And how do you do that? You have a deep well here with a proper capacity. In fact, you should calculate how many number of wells are required, what is its discharge capacity, what is the volume of water that you are handling. Okay. This is so much of water. See, the thing is, this at least this much of water is removed, right, like the whole area into that much meter cube of water. Okay. That where is it going? You have to have a proper drainage system, right, because that is very important. And you can see that here you are able to lower to this point using these two material, and also you have a piezometers which will tell you that yes, is the water table already, it will give you how much of water head is there, like is it 3 meters or 2 meters, it will give in water head. And so, if it is going to be more, then you should be worried, because it is going to touch. So, you must be able to control this by suitable pumping and operations. And you also have in the other thing that the so that it does not lead to lot of variations in water table, because this is a sandy layer, it should not say for example, there is lot of rains there, right. Suddenly rains come, and then the problem is that suddenly water table starts rising. But the problem is that if you have a good if you have nice grout curtains on either side, right, grout curtains on either side, the possibility is less. So, like the water takes more time, and you have to have some sort of technology or some sort of method in which you can handle to see that the pore pressure or the which is measured from these piezometers can be low. That is the actual point. How do you go about design is something that we should see, because sometimes I know that there are many contractors in India, but in fact they have been doing, in fact we get lot of inquiries, they have say for example in some place nearby, they have to go for an excavation of about 18 meters and the water table is at 9 meters, because 18 meters is something that you want to have a basement parking and all that, there is a good because of the land value that it has, you need to really go ahead with construction, because since the water table is there at 10 meters, I cannot say that I can't go beyond that, below that. So, one should be very careful, and people are ready, because whatever you recover in that process, like if the pumping costs are are okay, but your business is much better, many times higher, then it's fine. That's what people have been doing. So how do you design this is something that one should know. And what are the important parameters? The height of the groundwater table above the base of the excavation, right? Then the permeability of the ground surrounding the excavation. So these two, like what is the height you would like to handle, what is the permeability of this is an engineering parameter, this is then our own technical requirement. So depth of required groundwater lowering, so the water level should be at least about 2 to 5 feet below the base of the excavation. This is, it should be some sort of design criteria you have, because you can't do concreting here. This is a well point here. So now, okay, how do you get permeability? Because that is an engineering parameter, and actually people use based on the grain size distribution, you have some empirical formulas, like if you know the D10 of the material, I will get some K value. Then you should do laboratory permeability tests, you have borehole packer tests and field pump tests. Of course, accuracy and cost will make it little expensive, but the thing is that one should really do a good field test than using some empirical formula. That is the bottom line. And how do you get them? In fact, we know the how do you calculate using Darcy's law, you know the velocity, and then it is equal to the proportional to the hydraulic gradient. Velocity of water coming out of some of these things is proportional to hydraulic gradient, because that is head of water acting. So velocity you know, and then the porosity is another factor that you need to consider, and you can also calculate the flow of water that you should handle. All the pumps should handle this flow, right. So these are all the typical values of permeability. You can see that they are quite high. There is a big range of values, like depending on the type of gravel, clean sand, fine to medium sand and all that, and many things are there. Of course, as I just mentioned, depending on the D10 size of the soil in mm, we have a permeability coefficient one can get in centimeter per second. So this is some sort of actually people have used see, suppose you go to a site, you measure the D10 of the particle, like you have, say, normally you do a grain size distribution analysis, you also measure permeability. So if you are clever enough, you can plot all like this. You have so much data, in the particularly in field projects, you will have hundreds of grain size distribution curves, hundreds of values. So if you are able to plot a curve like this, that can be used for the design basis. In the same, you are handling a big site of 100 hectares, and you want to have some understanding of that. You may have understanding of shear strength properties, compressibility properties, permeability properties, then in situ tests, all that can be done. And for the same material that you have, you can really plot some relationship. Okay, I have this site, this grain size distribution there, what is the K value it can have? So this is what one can plot. Okay, this is very important. So you have constant head type of tests, where for the sands we use that, you calculate, you get the discharge, use the formula KL QL by HAT. Area is the area of the soil, T is the time of monitoring the flow for the required height, and you also have falling height at two different times. You calculate the height of fall, because what happens is that in permeability of the soils is clays are particularly so low that sometimes it is better to see what is the difference between two heads, what is the difference between or the height of drop at two time intervals, and calculate the K value, knowing all the other parameters. Of course, we have many number of tests in codes, like you have what is called rigid wall permeability, in the sense that what you do in the consolidation testing and all, you call it rigid wall permeabilities, and it is typically for sands and all that we use, and we do not really recommend for low permeability soils. So for example, sands and all that, if you are trying to do, it is okay, but if the permeability is less than 6, we try to go for flexible wall test. And what is the difference between rigid wall and flexible wall? I will explain. In rigid wall permeability, this thing, it's a simple apparatus. You have a tracks, the consolidation type of equipment. It's a rigid, right? It's a rigid. Whereas in you try to measure in a triaxial testing, the rubber membrane is there. So there is no leakage of the sidewall. Leakage is another big issue actually. So leakage along the sidewalls is possible, especially if the soil sample shrinks. If there is some volume change in the soil, then there is a problem. So many may use double ring equipment to discount sidewall leakage. In fact, there are some people, consolidation rings are there, right. So people have been using this rigid wall permeabilities to get K value, but it is better that people go for flexible wall permeability tests which are triaxial cells. There is no side leakage and effective stress varies, because the other advantage of the, like we know the difference between a direct shear test and a triaxial test, where under an effective stress you can calculate K value. What is the effective stress you can find out and calculate K value, that is an important thing. So this is a typical rigid wall permeability. People can, just if you have a sample which is in has rigid this thing, like, so you can measure permeability, there is no problem. But at the same time, like, you have all that arrangements for pipette and all that. You have some more equipment like this which are essentially for rigid wall, like sands and all that. Even compaction permeameter, like, essentially what you are trying to do is you put inflow and measure outflow, right. So that can be one, and this is a typical type that you have, okay. So what I am trying to do here is that you have the flow here, rigid, this is again, these two are rigid walls, okay, and water comes here and then goes to the porous stone and comes like this, and these are all so these are all some equipment that people have been using. Edge flow, sometimes there is a possibility what happens that edge flow is higher, right. We do not want corners, leakage and all that. So one should be very careful in the assessment of the K values, particularly when you are dealing with rigid wall permeameters. That is one thing, particularly when you are trying to deal with clays. You also have what is called double ring permeameter. Again, it is an equipment measures the permeant flow from the center and the perimeter of the sample concurrently. Flow is monitored with two pipettes. So again, that is one thing. What is flexible is here, like as I just said, triaxial. Different effective stresses one can apply at the top and bottom. Say for example, the effective stresses could be different, and this we are familiar. In a triaxial sample, there is a flexible membrane is there. You have a bottom cap and top cap, and measure the flow, right. Essentially, right, you can measure the flow. So there is some more equipment one can design, and it is not an issue at all, and essentially permeability measurements are quite important when you are trying to deal with drainage. Sometimes what happens, the permeability values, particularly in clays, it is very difficult to do. And what we see, particularly there is a problem, the thing is that the problem with associated with laboratory measurements of permeability have come I mean about 10 to 20 years back, because you have laboratory test results, they give some K value which is -7 or -6, -7, but in the field it is -4, like it is 100 times it is more. And the thing is that there is some what we are doing in the field lab was that to measure the Ki value, the K value, you apply a lot of heads, high heads, high hydraulic gradients not less than 50, 40 we create. Like if the sample size is 1 centimeter and you or base width is say 10 centimeters, you have at least 10 times or 20 times the head, and then the hydraulic gradient is very not practical. And so we try to make it to get some value we try to increase I, but it leads to cracking in soil, like high heads, like you can't sustain. Unrepresentative flow regime, like particularly in the lab, if you have high hydraulic gradient, it's not, then it may lead to sometimes internal erosion. Edge leakage in test apparatus, see sometimes all test apparatus are not perfect, and then there is a possibility of side leaks. So these are all typical values of hydraulic gradients recommended. Okay. So the thing is, one should not say if the K value is in this range, right, -3 to -4, the hydraulic gradient should be maximum 2, or if it is -7 clay 30, hydraulic gradient could be 30, but it should not be more. What happens, as I just mentioned, internal erosion of the soil particles take place, and it leads to wrong values, like K values will be totally, sample would have failed, because internal erosion means internal shear resistance is lost, there will be all particles will be floating under water, and you measure permeability and it will be very high value, it will be misleading, it is not a equilibrium condition, right. So that is the reason you go for field testing, and the way that we do the field testing is that like you have 2 observatory wells, and this is original water table, and you try to lower the water table, and H1, H2 are the observed values at a particular intervals of time, and these observation wells are at distances R1 and R2, and so what happens, because of this you try to measure periodically, and there is a drawdown that occurs. So how do you do this? Of course you have some sort of observation wells. How do you do this in practice is something that one should know. You have a plug, you have a pipe here, you have a threaded cap and all that, and sealed, you have a proper system, puddled clay or a bentonite plug. Actually this area, the water level, it should be in water, it should be allowable, permeable, you can see that it is slotted. Here also you can see that the top, the bottom portion is slotted, and there is a plug. So water enters here, or water, whatever is that, there should be a provision for water flow, so that you are pumping out, right, you are removing the water from that, and then this will measure the actual levels. So this is an important point in the observation levels. This is actually a standpipe, the standpipes with the slots at the bottom portion or wherever, if this is if the area is here, wherever you place, if this area is permeable, then have slots there, see that the slotted area is in the permeable strata, like sand and gravel back, all that is there and all that. Okay. So these are all some sort of expressions that one can use, like the discharge measured, and then R1, R2 are the radius, and then H1, H2 are the heights, the heads. So of course there are many equations that people have developed, like this is one Dupit theme approximation for single well, phreatic line, how it changes. Actually this one thing is that here H is this, what we saw was at any point, but this H is related to this where this head at which this is actually the depth, actual depth of the water table. Okay. So this is another expression that we have where we have so that way R naught is related to that, like influence range we call it, R divided by R naught is the radius, H is the height, and the HW is the water drop at any point, and using this expression one can calculate Q, and once you normally measure this Q value, and once you know the Q value you can get K, right. So there is another expression for the height of free discharge surface, there is some sort of equations that people have proposed, and how do you get this influence range, some expressions are available, R equal to like influence, that radius is in this form, and depending on the K values and the height of drop, And this is another important thing that I would like to just tell and then close today with this lecture. Actually, as I said, well points, well 1, well 2, well 3, there are 3 wells, okay. And then this is a point P at which water is to be removed, and then there are distances, situated distances h1, x1, x2, x3, right. So, our objective is, now most of the time, say for example, this is an underground basement, some place you would like to excavate, remove water, how much of water is to be there. So, you have to design well points properly with their distances, and you have an expression for it, okay. Pi k into h square minus y square by ln r minus 1 by n, n is the number of points, into ln x1, x2, xn, and then circular arrangement of wells. Suppose this is one arrangement that you have. Actually, this is a special case, and if all the x1, x2, x3 all are equal, then you can use this expression where a is the radius, right. Suppose you are trying to have a circular area or a square area and all that, you can just use some sort of well points everywhere and measure them, and then see that your discharge is in such a way that y, whatever is the y, y is you are trying to monitor this y and all that, and see that you are able to design with well points proper system, and you have a multi wells here, right. So, with this I think you are able to understand what is this dewatering systems, and actually see the dewatering is an issue, and this is what we say, like I was just mentioning that you have mechanical modification, you have a hydraulic modification, means you are trying to remove water. By removing water, you are increasing the strength of the soil, and PVDs is one type where you try to remove the soil, accelerate the consolidation, and then design it properly and then do that. That is one situation. In other cases where you have to do dewatering, this is one case where one can effectively do this using some proper concepts of permeability and pressures, and some sort of design can be given. And again, one should really monitor this, like we monitored settlements in pore pressures in the PVDs or sand drains. You have to measure again here water levels and see that whatever is designed, everything has to be monitored properly, okay. So, with this I conclude. Thank you.